What the Dance Dance Revolution? In the arcade, DDR player, stay here. And the player already has a foot on the correct arrow, then the player is awarded 1 lazy point. If neither foot is on the correct arrow, the player moving more than 1 foot at any given time. Moving either foot when the player is already stepping on the correct arrow. You're given a sequence of A of n rows. Assume that your left foot starts on and your right foot starts on right, and you have memorized the entire sequence of arrow. Okay, yeah. N divided by 4 lazy point straight around. I think I can do this. Maximum number of lazy points you can earn around. That's pretty interesting. Very much connect chat.
Playing from iPhone.
There's a lot of us. Alexa, turn volume to the minimum. Alexa, play some lo-fi music.
Lo-fi beats from Spotify.
showing that it's always possible to earn at least. How do we show that? How do you show this? So you have change the thickness. So for any sequence of numbers, so the worst case scenario, so you'll always be, how is it always possible to earn at least n over 4 lazy points during a round of DD? What? Is that what it looks like? Whatever. So if we start here, the next one's up. Go here. There's 0 lazy points. And the next one is here. And I guess we can put one. Huh? Yeah. But you can't. More than 1 foot at any given time. Failing to step on the correct arrow. Huh? During a round, as soon as your left foot starts on, you've memorized the entire sequence of arrows. So if it's this, how is it possible that I'm gonna get n over 4 lazy points? Because this is 0 out of 4 lazy points, is it not? either foot when the player's already stepping. So you can see this ahead. Okay. So here we're gonna move our foot here, like that. Boom. So no lazy point. But then call this left. Oh yeah, whatever. Left foot. Call this right foot. Left foot gets a lazy point. And then now so we move our right foot here. Then we hit it. But we know everything. So we fail here. Then this comes. And then move our left foot. I don't get it. Because how are you? You're not allowed to plan ahead unless it's the first move? What? Let's go on Ed Forum. See what they have to say. For question 1, should we find the sequence of survey results to use all sequence? Question 1, am I looking at the wrong assignment? Wait. This is question 3, but it's called question 1. Oh, this is question 3. Oh, no matter. Let's go to question 1 then. Sayonara. What does that sound? What? It's possible to add n over 3 per round? Show us how the student is feeling. You're going to make a report which uses one of the responses each day. Sequence of responses R1 to R. Yeah, technically speaking, you want to go to 5 if you have no knowledge, but we do have knowledge. You must have n less than or equal to 4 and k less than or equal to 3. Oh, so 3 students and they all have 4 responses. And then choose a sequence with the minimum fluctuation. Bro, that's easy. That's easy. Counter examples are easy. S1 is so 1, 2, 3, 4. Oh yeah, we'll just have a 10, right? S2 will equal start with S1 1. What is S1 1? Is that just the first one? Like, that's what I think. Oh, okay. Actually, that's a fair one. Wait, how could that be wrong? 9.9. Oh, they're irrational. That's pretty funny. But like, and then choose the sequence with them. Then for each subsequent day, choose the server song closest to the previous one. Repeat by starting at each S21. I'm not really sure what S. Repeat by starting. Oh, what? I don't even understand this algorithm, bro. They gotta have a better way of explaining it, G. Then for each subsequent day, choose the server closest to the previous one. Repeat by starting at each student, and of these, choose the sequence of minimum choice. Alexa, pause music. I don't know if I've understood it. My thing is just to go. There's no way that's right. It can't be that easy. Not for 6 marks. compute by starting at each. Huh? That can't be 6 marks. What's going on? Whatever. Design an O and K squared outlet to find the minimal fluctuation of an optimal sequence line. The sequence of set responses used to achieve this fluctuation. You have to actually find the sequence of responses without actually finding them. You can do that. I don't even know what's going on, dude. K squared O n K squared. K shrinks over n days. O n K squared, so for each student you So for each student, you look at every other student.
風長き届けの行くよ今までの話
It returns an nth-centered hexagon.
Huh? What? What the frick?
The natural choice for the subproblem is as follows. For each I, one. also working.
What the frick? This means nothing to me.
Do I need to watch the lecture? Probably. What the?
Hello everyone, welcome to tutorial 6 or tutorial 7 of Comp 3121 or Comp 9101. Today we will be starting dynamic programming, so this will be the first of 2 tutorials on dynamic programming. And this week we will mainly be focusing on one-dimensional dynamic programming problems, whereas next week we will introduce a second parameter and describe how you will want to think about coming up with algorithms for a problem that requires two-dimensional dynamic programming. Okay. So let's have a look at our first problem. So a subset I is said to be independent if I does not contain any pair of consecutive integers. So I is some subset of 1 to n. So if I take the set 1, 4, 5, 9, then I can take the set 1, 4, or I can take the set 1, 4, 9, etc. And these will form independent sets. So I can't take 4, 5 because these are adjacent. Our task is to find the maximum sum of the values that come from an independent subset I of indices. So here we are sort of given, well, one thing, right? We're given an array, and we can associate an array, the elements of the array, by its index. So for example, A2 is associated with A1, 4 is associated with A2, so on and so forth. And our goal is to pick the set of indices such that the set of indices form an independent set, and the elements that correspond to our indices is maximum. The sum of the elements that correspond to our indices is maximum. So the first part of the problem asks us to analyze why the following proposed greedy algorithm does not work. So the natural greedy algorithm is to basically pick the largest element and then remove its neighboring elements, and then we just repeat. So let's take a look at an example. It might help to look at an example that works, and then we'll look at an example that doesn't. So if I take the set 1, 4, 2, then there are 2 independent sets that I can choose. Or there's a couple, but there's the one that we want to look at is 4 or 1, 2. Obviously, we can also have 1 as its own independent set. We can have 2 as its own independent set. That's okay too, but these are clearly suboptimal, so we just remove that. Okay, so if we go ahead and do our greedy algorithm, then notice that our greedy algorithm will pick this independent set. Clearly, the index is an independent set. A singleton is an independent set by default, and the other collection is 1, 2. Well, if we go through our greedy algorithm, we're not allowed to choose 1, 2. And so you can kind of see that 4 is maximum. And so our greedy algorithm works on this example here. For an example that doesn't work, so the insight behind why this one worked was because the element that we picked was actually larger than the element by its side. So then we could have something like 1, let's see, maybe not 1. Let's do 2, 3, 4. So if we look at this example here, we can see that our greedy algorithm will choose the 4, and that will be it. So the greedy algorithm will pick 4, whereas the optimal solution is to pick 2, 3. Because these elements here, 2 and 3, they are not adjacent to each other, and so we can choose 2, 3 as another independent set. And this independent set is greater than the independent set that the greedy algorithm chooses. Cool. Okay, we will now design a dynamic programming algorithm that solves this problem. So what sort of information do we need? So the first thing we want to do is to think about what pieces of information that we actually want. If we look at an example, let's say 1, 4, 3, 8, 2, 6, and we try to construct an independent set out of this. What sort of elements, or what sort of pieces of information should we require to store so that we have this optimal substructure and this and the other property that a dynamic programming algorithm provides? So a good way to think about dynamic programming in general is to think about it in terms of maybe the shortest path or the longest path along a directed and acyclic graph. And the reason why this is useful to think about is because whenever we talk about dynamic programming in general, we need to talk about the algorithm in relation to its subproblems. And one of the things that we need for the subproblem is this acyclic nature. Because if we know that a subproblem, let's just say subproblem 1, let's just say this depends on subproblem 2, and let's just say subproblem 2 relies on subproblem. Now, if subproblem 3 happens to rely on subproblem 1, in other words, we get the cycle, then in fact we can never resolve any of these 3 subproblems, because if we want to resolve subproblem 1, then we need to resolve subproblem 2, but then to resolve subproblem 2, we need to resolve subproblem 3. But then to resolve subproblem 3, we need to also resolve subproblem 1. So there's no way to be able to solve any of these subproblems. So one of the key elements of a dynamic programming algorithm is the order in which we solve each of our subproblems. And this relation requires our ordering to be acyclic. So we need this acyclic relationship between subproblems. So if we want to be able to represent a problem in terms of its dynamic programming stages, then we want to be able to consider how different subproblems relate to each other. So let's take a look at the example array that we have here, and see if we can break it up into smaller constituents, so that we get this sort of nice acyclic property here. So the most natural way to represent the array is via a graph. So let's imagine each of the elements of my array as a node, and we want to be able to store something inside of each of the nodes, such that we can relate each of the subproblems together. So 1, 4, 3, 8, 2, and 6. So each of the elements becomes a node. We don't know what to store. Well, we don't know what these nodes actually represent. But so far, let's just leave it as these are the elements of my array. Now, if I want to construct an independent set out of this, then there are some things that we need. The first thing we need to know is, if we know that 1 belongs in my independent set, I know for a fact that 4 cannot belong to any independent set that also includes 1. So we can construct an arrow from 1 to any element where they are a compatible independent set. So for example, 1, there can be an arrow from 1 to 3, which means that 1 and 3 are compatible elements in my independent set. Similarly, 1 and 8 is also a valid independent set. And 1, 2, 1, 6. So as long as they're not adjacent to each other, then that's perfectly fine. And what we're going to do is we're going to only consider the arrows in one direction. Right? We're not going to consider arrows in two directions, just because we want them to be acyclic. So we want to have an order. Obviously, you can start at the end as well, but we'll leave it as the front for the time being. Now, if we move on to 4, then notice that the only element where you don't have an arrow is 4 and 3. So there's no arrow between 4 and 3, because if 4 is part of my independent set, then 3 can't be my independent set. It can't be in the same independent set. So there has to be an arrow from 4 to 8, 4 to 2, and 4 to 6. And you can kind of repeat the same thing, right? So 3 goes to 2, 3 also goes to 6. It's purple. And so 8 goes to 6. Cool. So now one of the things that we want to think about is, well, what do the edges represent? So that's one of the questions that we might want to think about whenever we're constructing this sort of acyclic graph. So what do the edges represent? So let's say that I have an independent set that includes 1. Well, that also means that I can have an independent set that includes 3, or 8, or 2, or 6. So if I have an arrow from 1 to 8, that means, well, they are compatible elements inside of my independent set. So I can essentially choose this path. And once I have this node, that means that there is an independent set that includes 1 and 8. Similarly, from 8, I can choose any of the elements where there is an arrow. So from 8 to 6, I can choose that as well. So that's perfectly fine. Likewise, I can also start at 4 and decide to add all the others. So one of the things we want to do is, these edges represent compatible elements in my set. Okay, so the edges represent the compatibility between 2 elements inside of my independent set. Okay, but then what do the nodes represent? So the second question is, what do the nodes represent? So what is one thing that we want these nodes to represent? Well, these nodes represent subproblems. So these nodes are actually my subproblems. And so therefore we need to find a way to describe what these subproblems actually say. Now this subproblem will basically say, what is the, well, so if I look at this particular element here, then this says to me that this is the largest independent set that contains this particular element. So if I look at one particular node, this particular node says, I want to store the largest element, or the largest, or, yeah, so I want to store the maximum value independent set that ends at this particular element. Right? So if I look at this particular element here, that means it's the largest possible independent set that ends with this element. So that gives me a very nice way to characterize my subproblem, and the edges therefore represent what subproblems I need to check to basically solve my subproblem. So for example, if I want to know what the largest or what the maximum size independent set ending with element 8 is, then I need to check all of these subproblems where there is an edge leading to 8. Right? And so, doing it this way allows us to then very easily construct my dynamic programming solution. So, this is my subproblem. So let op of I denote the largest, the largest value independent set that ends at element I. Or if we don't want to end it at element I, then what we can say is I guess using the first I elements. Using the first I elements. Right, so we don't necessarily need to end at 1, or we can just say, okay, well, this is the largest independent set, or the independent set with the maximum value, using the first element. Okay, so then, let's think about the recurrence. Let's say that I want to resolve this particular element here. There are sort of two options here, right? So if you want to use the first I element, then either you're going to include the last element, or you're going to include or you're not going to include it. So, either include element I, or exclude element I. So if we include element I, then if we look at the subproblems that we want to resolve, we cannot resolve, or we don't worry about this element here, right? Because if we know that we're going to add in element 8, then we only look at all of the compatible subproblems. And so, it suffices then to look at up to element I minus 2. So we look at opt of I minus 2. And so the value that we get in the end, is opt of I minus 2. Of I is just opt of I minus 2 plus whatever value that we get for the current element, AI. But on the other hand, if we exclude, then it suffices just to look at I minus 1. It's the same as looking at the subproblem where you don't even include element I, which is the same as looking at the first I minus 1 element. In other words, opt of I is just opt of I minus 1. And so, if we look at all possible solutions, then we're just maximizing over these two recurrences. So opt of I just becomes the maximum between opt of I minus 1 and opt of I minus 2 plus this element. Remember that we need our base case. Well, the base case is what happens when, so we need two base cases here because we have two things happening here in our recurrence. So we need opt of 1 and we need opt of 2. Well, opt of 1 is, well, just going to be the element itself. There's no reason not to take that particular element. And opt of 2 is just the maximum between the first two elements. Either you're going to take the first element or you're going to take the second. Now we have our final solution. The final solution is, well, what happens if you use up to all of the elements? So this would be opt of n, with the time complexity being the following. So to compute the time complexity, you need to look at two things. The first thing you want to look at is the number of subproblems. And then you want to look at the time it takes to solve each subproblem. So the number of subproblems that we have is, well, we have one subproblem for each element, so we have n subproblems, and the time it takes to solve each of the subproblems is O of 1, right? Because if we try to solve our recurrence, assuming that we've already solved for opt of I minus 1 and opt of I minus 2, then looking at opt of I minus 1 is a constant time lookup. Looking for opt of I minus 2 is also a constant time lookup. And looking for a of I, assuming we have constant time lookup for arrays, is just constant time. So it takes constant time inside of my max function, and I'm performing my max function once. So the entire recurrence is constant time, which means that what we're essentially doing is we're essentially doing a constant time operation for each of my subproblems. Because there are n subproblems, this will be n times O of 1, which gives me an O of n solution. And so the final time complexity for my algorithm is linear time. So that was question 1. Now let's look at problem 2. So in this problem, we will design an algorithm that counts the number of ways to form a bit string of length n, such that the zeros are always in groups of length k. So here they give you 2 examples. So if n is equal to 3 and k equals to 2, then we have 2 possibilities, or 3 possibilities. One where the zeros don't appear at all. These are still technically in groups of 2, because for something to be in group of 2, it means that if there exists a 0, then there exist 2 zeros. Right? On the other hand, if n is equal to 5 and k equals to 2, then we will get, I believe, 8 bit strings.
Is this not a combinatorics question?
Now notice that there are some that are grouped in groups of 4. This is also perfectly okay, because you can think of it as truncating it at these particular points, and these are still then technically in groups of 2. So you can have groups of 4, where you split each of the group of 4 into 2 groups of 2, so these are technically still okay. But you can't have something like 0, 0, 0, 0, 0, 1 or something, where you have a group of 2, and then the 0 is no longer in a group of 2. So it has to be in groups of 2 or groups of 0. Okay. And our goal is to design or describe a linear time algorithm that counts the number of strings such that the 0 bits are in groups of k. And again, we're going to follow the same procedure. We're going to think about each of the subproblems. We want to think about decomposing the problem into smaller parts, and then try to find a way to bring them all together. The difficulty with this problem is that the base cases aren't as clear as problem 1, and we will see why in a second. And lastly, we want to compute the time complexity. So what we want to do is we want to count the number of subproblems that we have, and we want to compute the time complexity for each of the subproblems, and that will give you the overall running time for the algorithm. Okay, so let's take a look at problem 2. So let's think about an instance of the problem, and then we're going to see if we can decompose it into parts. So let's start by just looking at the case where n is equal to 5 and k is equal to 2. So if I take 1, 1, 0, 0, 0, 0, wait, that's 6. 1, 0, 0, 0. Okay. So we want to count the number of ways where we have a length n string. So we have a length n string such as the zeros are in bits of in groups of 2, or in groups of k. Okay. So how would we break it down into smaller parts? So what are the things that we want in order to count the number of strings of this form? Well, one natural way is we want to keep track of where we are in the string. So let's say that we are currently this part of the string. If I then add on a new character, how many total possibilities do I have? And then, hopefully, by the time we get to the very end, we will count the total number of strings. Okay, so that's a decent approach. Let's see how we can mold it into a dynamic programming algorithm. So each of my subproblems is going to be, well, I'm going to keep track of where I am in the string. So let num of I denote the number of strings, of bit strings, of length I, such that the zeros are in groups of k. Okay. So let's start at the very start. So let's start with the first character. If I then want to add on a new character, there's only 2 possibilities. There are only 2 possible characters that I can add, because it's a bit string.
1 or 0.
I can either add a 0, or I can add a 1.
Yay.
If I add a 1 to my bit string, so let's just say I have a 1, so I count the number of ways where the first character, where we have a bit string of length 1, and the zeros are in groups of k. If I then want to add on an additional character, let's just say I add on a 1, then all I need to do is append each of my bit strings of the previous length with the 1 here. If I add on a 0, so this is easy. If I add on a 1, that's very easy. If I add on a 0, however, I need to be a little bit careful, because if I just add on a 0 after the 1, then my zeros are no longer in groups of k. So I need to think about what the subproblems I want to look at are if I were to append these zeros. So there are two options for my recurrence. So remember in the previous exercise we looked at the case where we either include an element or we exclude an element. We're going to do something similar, but we're going to either append a 1 or append a 0. And if we append a 1, that's easy because there are no issues with just appending a 1. If we append a 0, we need to be a little bit more careful. So if we append a 1, what happens? Well, we're just counting the number of valid strings so if I want to look at all of the bit strings of length I, where the last character is a 1, then every possible combination that I had before was also valid, because the 1 doesn't violate any of the conditions that we need, that we have in the problem. So if I append a 1, then there are no issues. Then opt of I, so the number of bit strings of length I is just the same as the number of bit strings of length I minus 1. Right, because if you imagine a bit string of length I, then all of these elements, so we look at all of these strings, these are all valid strings. All of them end in a 1, well, there are certainly no issues. If it were a valid string of length I, then certainly it has to be a valid string of length I minus 1, right? Because each of these strings have to have zeros in groups of k, and because I'm just adding a 1, it doesn't destroy any of the bit strings. Cool. Now, if we append a 0, if we draw it out again, remember that we need all of the bit strings to have length I, and the zeros have to be in groups of k, which means that each of these elements here, okay, I'll draw. So 0, so which means that, let's say, each of these elements here also have to be zeros. Because if they weren't zeros, so say that if this was a 1, then I no longer have valid bit strings. So each of the elements here, 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 and here also have to be zeros, which means that it's the same as counting the number of valid bit strings of length I minus k. So you can imagine that these are all zeros, there are k zeros. It means that we have I minus k many spots to go, and if each of these are valid, then all I need to do is append k zeros right at the end, and I also get a valid bit string. So in the same way, where appending a single 1 is perfectly fine, appending k zeros at the end of my bit string is also perfectly fine for any combination of valid bit strings of length I minus k, right? Because I minus k plus k zeros give you a bit string of length k. And so the number of valid bit strings if I append a 0 is just opt of I minus k. Right, so I just need to count all of the possible bit strings of length I minus k, and then I just append k zeros at the end, and that does not violate our condition anymore. If we included two little zeros, say that we included something like k minus 1 zeros, then we need to be a little bit careful because the last element of my bit string could be a 1, in which case that will violate my condition. So we need k zeros at the end. Cool. So because a bit string can only end with a 0 or 1, and it can't end in both, these two cases are actually disjoint. So the case where we end in a 1 and we end in a 0 are actually disjoint cases, which means that if I want to count the number of bit strings of length I, such that the zeros are in groups of k, then this is just the case where we append a 1, which is I minus 1, plus appending k zeros at the end, which is the same as opt of I minus k.
Oh, okay.
And this subproblem is good because it also allows us to easily find what the final solution is, where the final solution is opt of n. We want to find all bit strings of length n, such that the zeros are in groups of k, because the length of my string is the only thing that changes. Well, opt of n gives me the final solution. Cool.
What?
Okay, so now comes the difficult part. So we've looked at the recurrence, we've looked at the subproblem, now we need to look at the base case. Or in this case, base cases. So if we look at our recurrence, we need a couple of things. We need opt of I minus 1, and we also need opt of I minus k. So if I look at opt of j for j, right like this. So for j between 1 and k, right? Well, the only possible way is, oh, actually, okay, need to be a little bit careful here. So for j between 1 and k, where we include 1 but we exclude k, then the only possible way is everything has to be a bunch of 1s, because the moment we have a 0, then we need k zeros, right? So for the case where j is strictly smaller than k but larger than 1, opt of j is 1. There's only one possible string, and that's just all 1s. For the case where j is equal to k, in other words, we have opt of k, then either we can have all 1s or all zeros. So there are actually two ways here, right? Because either you're going to have all 1s. If you have a 1, then you have to have all 1s. Or you can have all zeros.
Yeah, that makes sense.
So there are two ways. So both of these can be my base cases. And both of them will be reached at some point, because if it's not opt k, then it has to be something strictly smaller than k. And we can also set opt of j equal to 0 if j is smaller than 1. That's also perfectly fine. So that just makes sure that if we ever do get a case where I happens to be smaller than k, then and we're still in this recurrence, then then we're okay. But that should never happen, because if it's a case I is smaller than k, we will essentially jump into this bullshit here, where opt of j. But if you want to be extra careful, you can also just say that, well, if you have invalid indices, then you just set it to be 0. That's perfectly fine as well. So that would be your base cases. So it's a little bit harder because you need to carefully think about which are valid base cases. And then what you can also do is, so and another way to basically map out this solution is to say, well, by convention, you can also set opt of 0 to be 1 if you wanted to, and then opt of j to be 1 for all j smaller than k. And larger than 1. It's also perfectly fine, because that essentially breaks into opt of k equal to 2. Yep, so there are many ways to model this same thing. And the last thing we want is our final solution, as we discussed before, is opt of n, because that gives us all of the bit strings of length n, such that the zeros are encrypted k. And the last thing we want is our time complexity. So remember, it's just a number of subproblems multiplied by the number of, or the time taken for each of the subproblems. Time for each subproblem. So the number of subproblems that we have is n, or something proportional to n, and the time for each subproblem is over 1, right? Because if we look at our recurrence, we assume that we've already stored this portion here, and we've already stored this solution, so each of them are just constant time lookups. And so the time taken to solve that particular subproblem is constant time. There are n subproblems, so the final running time of our algorithm is O of n. Again, we have n subproblems, each of them takes O 1 time. So that was problem 2. So this one had a harder base case,
What the
but a slightly easier recurrence. Now we're going to look at a more interesting problem. So you are emailed a text file containing important meeting notes. Unfortunately, the text file was corrupted and all of the white spaces of the text have been removed. So all you see is just a string of characters with no spaces. Fortunately, your company is very good at keeping tabs with words that are mentioned during meetings and have devised a lookup function. The lookup function acts as an oracle and returns true if and only if the string is a valid word. In other words, if you give the machine a word, it will spit out true if it is a valid word, otherwise it will spit out false if it's an invalid. And our goal is to design or to describe a quadratic time algorithm that determines whether a given string forms a valid text by placing spaces in between characters to form a string of valid words. So we define a valid text to be just a string of valid words with spaces. Oh, so this one's a little bit harder. It's not immediately clear what the subproblems could be. So let's try to break it down into smaller parts and see how we could intuit what subproblems we want to pick and how we will then solve it in quadratic time. Problem 3. So let's say that I have a string, and the dictionary is hello, right? So I know that the valid words are hello there. How could I tell the algorithm where to place it. So if I look at this, if I look at the string, then notice that a valid text will occur when, if you see a valid word, the remaining portion of your string also forms a valid text. So to sort of see what's happening here, let's say that I look at this entire string and I look at each of the particular characters one by one. So let's say that I look at H. I say, okay, well, if I feed the machine H, it's going to spit out false. So that means that H is not a valid word, which means that I can't place spaces. I can't place a space here. Because if I place a space here, then what essentially happens is I get one part which is an invalid word, and then the rest is some string that I don't care about. Okay, so let's move on. So if I look at the first two characters then, and I feed the machine the word, it's going to spit out false. It's not a valid text according to the dictionary. So it's not a valid word according to my dictionary. So I can't place a space here. Because if I place a space here, then well, I get one part which is an invalid word. Okay, now if I continue, what if I place a space in between the first three characters? So if I look at the first three characters, I feed it the machine, it's better no, so I can't place a space here. Okay, and we can kind of see that this will keep going up until you get to the O. So I look at these first five characters and I say, well, what if I feed the machine this word? Well, it will spit out yes. Cool, so it is possible to place a space here. So let's just keep that in the back of our mind, that it is possible to place a space here. So now we've broken the string into essentially two halves, right? This is some valid word, this is some word that we can place a space, so this is okay. Now we need to look at this portion. And our goal is to basically figure out, is there a way to place spaces such that this remaining portion is a word, or is a valid text? So let's continue the same argument. Well, can I place a space here? Well, T is not a valid word, TH is not a valid word, so I can't place a space here. THE is not a valid word, THER is not a valid word, oh, THERE is a valid word.
Right, look at his R.
This is also a valid word, in which case I know that I can place a space between the O and the T, and I get a valid text. Okay, so this is sort of like the idea that you might want to have. Now we need to think about how to design an algorithm more generally to do this in quadratic type. Okay, so what we did was we looked at all of the possible ways we could place a space. And we said, if there was a single place where we could place a space, so if there was a single position where we could place a space, then we've broken it down into two parts. We've broken it down into a word that we know is valid, and the rest of the string. And as long as the rest of the string is a valid text, then the entire string itself must also be a valid text. So, this gives us a nice way to describe a subproblem. So, now we have a way to describe the subproblem.
Huh?
So let's say valid I denote whether the first I characters form a valid text. In other words, valid of I is true if and only if the first I characters of my string forms a valid text. So if I look at my string as s of 1 to up until n, then basically what I'm saying is s of 1 to I is true. Well, this is not true. Valid of I is true. If and only if s of 1 up to I is a valid text. Okay. Now remember how we verified that s of 1 to I is a valid text. We said if there was a way to place a space such that first say j characters is a valid word, and then the remaining portion is a valid text, then the entire string must also be a valid text. So what we're going to do is we're going to say valid of I is true if and only if there exists some position. So valid of I is a valid text if and only if there is a position where you can place a space. Let's call the position j to place a space such that maybe the first j characters is a valid word. So s from 1 to j is a valid word, and we also require the remaining portions to be a valid text. Actually, so there is a problem with doing it this way, and that's because valid of I is denoting whether the first I characters form a valid text. So if we're looking at the first j characters here, then we're going to run into some problems. So instead, what we're going to do is we can just flip our consideration. So instead of looking at s of 1 to j being a valid word, what we're going to do is we're going to then say s of j plus 1 to n, or to I, sorry. To I is a valid word, so we're looking at the last portion. So going forward and going backwards to check if it's a valid word is exactly the same. You can decide to go from the back, or you can go from the front. That's perfectly fine. So valid of I is true if and only if there exists some position j to place a space such that s of j plus 1 to I is a valid word, and valid of I, or valid of j is true. Right, so in other words, the first j positions is a valid text, and then the remaining j characters, so the remaining I minus j characters is also a valid word. And if this is true, then this entire thing here, this entire string is valid. So that's our goal. Okay. So let's think about how we can do this. So the first thing we want is the existence of some position. So in other words, we can try every single combination. We can try every possible position, and we'll check each of them one by one. So we want to have maybe valid 0. Maybe the entire string is a word. That's perfectly fine. And s from 1 to I. So that's one possible way. Or valid 1 and s from 2 to I. Okay, so if this is true or this is true, or valid 2 and s3 to I is true, or and so on and so forth, up until valid of I minus 1 and s. Okay, so as long as there is some combination where it's true, then my entire string is true. Or my entire string. So as long as one of the conjunctions is true, then we're done. And this is how you can represent this. Obviously, this is too cumbersome to write, so what we can do is we can actually write it a bit more significantly. So what we're going to do is we're going to write it like this. Valid of I is going to be the disjunction where you're ranging from j equals to 0 to I minus 1 of valid j and s from j plus 1 to I. And this is just the same as saying valid of 0 and s of 1 to I is true, valid of 1 and s of 2 to I is true, and so on and so forth. So as long as one of these is true, then valid of I is true. And valid of I is not true as long as this entire thing, every possible partition is not true. Yep, and so this gives us a nice recurrence for my algorithm. Now we're going to look at the base case and the final solution. So we're going to look at the base case. So remember what we had in our recurrence was valid of 0. So the base case for valid of 0, that's just going to be true by default. If you have an empty string, by definition it is a valid text, so that's perfectly fine. And final solution. So the final solution, well, you want to basically say, is the entire string a valid text? So that's just valid. N, and my final running time. So if I want to compute the time complexity, there are firstly n subproblems. So you can think of it as one subproblem for each position that I can place my space. So there are n subproblems, and the time taken to solve each of the subproblems, well, what we're doing here is we're going through each of the possibilities, each of my subproblems. So at most, you're going to be doing O(n) work. A better way to think about the runtime is, if I look at my base case, there's only one comparison that I'm making, if I look at the second case, there's two comparisons that I'm making. If I'm looking at the third case, there are three comparisons up until n, right? So there are at most, say, n, or roughly n comparisons that I'm making. So in total, my entire running time would be 1 plus 2 plus 3 until n, which is n times n plus 1 divided by 2, which is
What?
big data of n squared. And so the total running time is O of n squared, and you can think of it as the number of subproblems is n, the time taken to compute each of the subproblems is at most O of n. Right, so n subproblems with O of n work gives you your O of n squared solution, which is also what we have here. And that basically wraps up dynamic programming for this week. We will be covering two-dimensional and multi-dimensional dynamic programming in next week's tutorial. So these problems will be a little bit harder in the sense of how would you construct a suitable subproblem to solve a multi-dimensional, well, a problem that requires multi-dimensional dynamic programming.
What the frick just happened? Who's this? Is that Gerald?
How's the volume? Is it good?
What the frick?
I guess we'll get started. So hello guys, welcome to Comp 3121, Comp 9101. As you may expect, I am not Katie, so I will be covering for Katie just for today's lecture. Yeah. So
Damn.
let's get started. So today we'll be covering.
Bro is so goated he can
dynamic
actually
programming.
lecture.
And the first question is, what even is dynamic programming, right? Like, it's a very fancy term, but you know, what is that? It turns out this name doesn't really have any meaning, right? So dynamic programming was basically developed, and it was named dynamic programming because the inventor thought it was like that. That's literally it. It's the actual reason why it's called dynamic programming is because back when it was first being developed, the people developing it didn't like mathematical research, so they tried to basically find a way to basically say this is what we do, except we don't want to call it research. So programming was sort of invented. Programming itself is not really the programming experience in the comp course. This is actually referring to programs. So if you do any sort of operations research or anything, then you'll come across things called programs or systems, which is basically a sequence of steps that you have to take. And it's dynamic because, you know, there's no other way to describe it. It's just literally dynamic. So the name dynamic programming is born. So let's sort of discuss what even is dynamic programming about, why it's useful, and then we'll jump into some examples of dynamic programming. So back when you first looked at algorithm design techniques, the first thing you would have come across is what we call divide and conquer. And divide and conquer was a recursive algorithm used to basically split the problem up into smaller problems and then combine all of your problems together in a way where you get your final solution out of solving all of your subproblems. So if we look at divide and conquer, what we really did with divide and conquer was to split it into at least two subproblems. And then from splitting the problem into two or more subproblems, you solve each of those subproblems independently. You solve so you solve each of the subproblems independently, and then to get your final solution, you just combine everything into your final solution. Now, with a divide and conquer algorithm, this step here means that you actually solve each of your subproblems independently and separately. So each of the subproblems are not related to each other at all. So these are separate. So if you think about an example of a divide and conquer algorithm that we saw maybe in the tutorials or in the lectures, we had basically a grid with one square missing.
Oh, I remember that one.
So maybe something like this. And our goal was to essentially tile this entire grid with these L-shaped dominoes. And does anyone remember how we actually solved this?
No, I do not.
So our goal was to basically tile this using these L-shaped dominoes.
I kinda remember.
Remember what we did was we split it into 4 parts. Right? So we split it into 4 quarters, and then we said, okay, in the quadrant that doesn't include the missing square, we're just going to place the domino in the other 3 remaining quadrants. Now, when you're thinking about the algorithm design aspect, notice that each of these remaining subproblems.
What the? They're basically.
For each of these remaining subproblems, you don't actually require the solution to any of the other subproblems. So to solve this subproblem, you don't need the solution to this subproblem. And to solve this subproblem, you don't need a solution to this subproblem, etc. So each of these subproblems are actually independent of each other. Now, sometimes when you're looking at a problem, it's not always true that all of these subproblems will act independently of each other. In fact, most problems you'll come across in this course or in other courses have problems where you can't actually split the problem into subproblems that are actually independent of each other. So we need another strategy to deal with the case where you have non-overlapping subproblems. And this is where dynamic programming comes in. So now we're going to introduce the idea of dynamic programming in the scope of defined algebra.
Wow, I already love Go.
Now, I like to think about dynamic programming as literally just brute force, but brute force done in a way where it's very clever. So when you're thinking about exhaustive search, or when you're thinking about brute force, what you're really doing is you're searching through all possible enumerations. So you're enumerating through all possible scenarios and then picking the best one, right? So for example, if I have a bunch of vertices here, oops, and I want to say, well, what is the shortest path? One way is to just go through all of the possible, if I say I want to have the shortest path from this vertex to this vertex, then one possible way is to just go through all possible paths and then pick the shortest one, right? Now obviously, that type of algorithm is very slow, because in the worst case, you can have exponentially many paths. And if you're trying to pick the best one out of all the exponentially many paths, then you end up with an exponential time algorithm. So instead what we could do is, instead of thinking about brute force, what we could do is, maybe there is some pattern in the way that we're solving the problems, and that allows us to reuse all of the subproblems as well. So let's have a look at a motivating example and kind of explore some ideas. So the first problem we're going to look at is Fibonacci. And this is a problem
Bruh,
that
of
you're
course.
familiar with, and this is the best sort of introduction to dynamic programming. So. Okay, so let's say that you're given f of 1 equal to 1, f of 2 equal to 1, and we can then recursively define the nth Fibonacci number. Right, so we define 2 base cases where f of 1 is equal to 1, so the first 2 Fibonacci numbers are 1, and then for every other possibility, or for every other integer, we're going to define our Fibonacci number recursively. It's just going to be the sum of the previous 2 Fibonacci numbers, and our goal now is to basically compute what the nth Fibonacci number is. So our task is to compute fn. Does anyone have any ideas for how we could solve this? For loops, yeah. You could use a for loop. We'll get to that in a second. We will just basically write a very naive recursive algorithm for it. So one possible algorithm is to just go, well, if n is at most 2, then we return 1. Otherwise, we return f of n minus 1 plus f of n minus 2. This is an algorithm, right? Is it correct?
Yes.
Yep, so why is it correct?
Oh, the why is it correct? I don't know how to answer that.
Yeah, you don't need to go in depth. It's literally just by definition, right? Because by definition, the Fibonacci number is, for our base cases, we have the first 2 Fibonacci numbers being 1. That's covered in this base case here. Otherwise, we're going to return f of n minus 1 plus f of n minus 2. And so what we're doing is we're returning whatever our nth Fibonacci number actually is. So this is obviously correct. What's the running time? How fast is this algorithm? It's going to be much faster than 2 to the n. But yeah, so you can see that the time complexity is t of n, which is equal to t of n minus 1, plus t of n minus 2. And then we're going to assume that all of the operations are constant time. So everything we do in between is just constant time. Now this does have a closed form, but this is going to be much faster than 2 to the n. And so you can see that computing the nth Fibonacci number is very, very inefficient using this algorithm. Faster. It's going to be something like 1 plus square root of 5 over 2. Something like that.
What?
Okay. Yeah. And the exercise for you to do at home is, well, how long does it take for you to compute the 50th Fibonacci number if you just run this algorithm? So how long
Bro, why is this guy trolling? I ain't gonna time that. Trying to
How
break
does
our
it change
computers,
if
bro.
you use F50? If you just use the naive algorithm, my question here is how long would it take to compute the 50th Fibonacci? And you can see that n equals to 50 is very, very small. But what you'll find is that your computer would be running, it will be running quite slow to just compute the 50th Fibonacci number. Does anyone know why this happens? Exactly. So you're doing a lot of duplicated work, right? Let's have a look at an example of why that would happen. So let's say that so let's say that I want to compute the 8th Fibonacci number. Your computer can do this, but let's just look at a computation tree. So if I want to compute the 8th Fibonacci number, which Fibonacci numbers do I need to compute? Yep, the 7th and 6th. Okay, now if I want to compute the 5th Fibonacci number, which ones do I need to compute? 6th and 5th. And you can sort of continue this thing, right? Until you get to your base cases. Now, if I look at the 7th Fibonacci number, it looks like I need to compute the 6th Fibonacci number and the 5th Fibonacci number. But then I also need to compute another 6th Fibonacci number here as well. So what's actually happening is I'm computing the 6th Fibonacci number here, and I'm also computing the 6th Fibonacci number here. So it looks like we're recomputing the same thing multiple times. And this is what causes our algorithm to be really slow. Because we need to compute the 6th Fibonacci twice. How many times do we need to compute the 5th Fibonacci number?
Twice as well.
3 times. So we're
Twice.
So I need to compute the 5th Fibonacci number here, and I also need to compute the 5th Fibonacci number here.
Yeah.
So, is there a way to make this faster, do we think? Exactly. So for the people who couldn't hear it, what we can do is instead of recomputing these values over and over again, we could just store it into a table. And once we store it into a table, we just need to look it up every time we need to compute it. So instead of computing the 6th Fibonacci number twice, what we can do is we can compute it once, say here, and then once we compute the 6th Fibonacci number, we store it into a table. So let's have a look at a faster algorithm. So, and this technique is called memoization, where once we compute something that we've never computed before, we store it into some sort of table, some sort of array, and then once we need to recall it again, we just read the table. We don't need to recompute it over and over again. So how could I write an algorithm for the memoized version, where instead of recomputing the same thing, what we're doing is we're going to store it into a table.